Welcome to this video for the Expanding Universe section of the R Dynamics Universe unit, and here we're looking at Redshift, following on from our earlier video on the Doppler effect. What are we looking at? Well, we're looking at that the Doppler effect was the observation in terms of sound, but it also applies the same principle in terms of light radiation. And so the Doppler effect gives rise to redshifts or blue shifts. And we'll use those redshifts and blue shifts to be able to calculate the redshift value and also the recessional velocity of galaxies. So astronomers believe the universe is expanding and that all points in the universe are getting further apart all the time. And we know this by looking at redshift. So redshift is an example of the Doppler effect. And what we've got in the picture there is we've got that the spectral lines have been shifted to the right by the particular galaxy that's imaged at the bottom there. So all the lines, the black lines on the line spectrum there, are moved to the right, and so they're shifted towards the red end of the spectrum. And that's because the stars are moving away from us. In the same way that we know that the frequency of the sound gets lower as the object moves away from us, the frequency of the light gets lower as the object moves away from us. And the red end of the spectrum, remember, is the low frequency end of the spectrum compared to the much higher end of the spectrum, the blue end. If stars move towards us, then we would see a blue shift. So we'd see those same spectral lines that are then all shifted by the same amount to the left is how they're normally displayed, to the blue end of the spectrum. And that would be showing that they're coming, the galaxies and the light is coming towards us. And so we get that effect in the same way that we got the Doppler effect for objects coming towards us with an increase in frequency. So the light emitted by any star is made up of line spectra based on the elements that are present in the star. And in the 1920s, Edwin Hubble observed the shifting light and looked at particular line spectra. So it's possible to look at the emission spectra of an element such as helium here on Earth, and you can see the emission lines that are there. So we've got a big strong yellow line and some red lines and blue and green and violet colors of light. Remember, these lines are occurring because we've got a transition of the electrons within the helium atom jumping from a higher energy level to a lower energy level. Okay, so we looked at this in the particles and waves topics where we've got E equals HF, and so the higher energy jumps, the blue jump here will have a higher energy than the yellow jump here because it has a higher frequency. Okay, what we can do is we can look at a star that contains helium, and we can see those same lines are present as they are on the Earth, but all the lines are shifted slightly to the right. Now this can mean that the color of the light also changes. So usually we just have lines for the line spectrum rather than colors, because if the shift is big enough, then they would be changing from one particular color to another one as they shift towards the right here. Okay, so we've got a galaxy that's redshifted moving away slightly, which is shifted a little bit, and one that is moving away faster, which is redshifted even more. So it's the shift towards the red end of the spectrum of these spectral lines. Okay, so we can also have the same relationship there, that the redshift is equal to the speed the galaxy is moving away divided by the speed of light. Now note that redshift is a ratio, so there's a ratio of the two speeds or the ratio of the wavelengths, so therefore it doesn't have any units. Redshift is also true for galaxies that are traveling at non-relativistic speeds, so speeds less than 10% of the speed of light. And once we get galaxies that are moving away at greater speeds than that, then we have to make further, more complex calculations. So the redshift has no unit. If it's a positive value of Z, it is a redshift. It is possible that some galaxies could be coming towards the observer, and that would give a negative value, a blue shift. But for the pretty much all purposes, because the universe is expanding, then almost all values that we'll look at will be positive and a redshift. So let's look at what this means in a bit more detail. So we have light with a wavelength of 486 nanometers is emitted from hydrogen in the sun, and we observe that same light in a distant star with a wavelength of 496 nanometers. So it's redshifted, the wavelength has increased, and we're asked to calculate the redshift of the star. So, and then work out the recessional velocity. So how far away, how fast is it moving away from us? Okay, so we just substitute in those numbers into our relationship there, and we end up with a redshift of 0.021. Remember, there's no units because it's just a ratio. The recessional velocity, well, the redshift Z is equal to V divided by C, so the recessional velocity V will be the redshift that we've just calculated multiplied by the speed of light. So that gives us our particular value for how far this star and the galaxy perhaps around it are moving away from us. Okay, let's look at a second example. We've got a sample of gas that produces a spectrum with a wavelength of 658.5 nanometers, and a similar spectrum is observed from a distant star that is shifted to 677.9 nanometers, and we've got to determine the redshift ratio and the recessional velocity. What we would see is a diagram a bit like that. Okay, sometimes you may have to read off the values. There might be a graph that goes with this, a scale that goes with these spectral lines. So you have to read off the value of a particular line and then work out the redshift from that. So we're going to just substitute in our values to work out our redshift. Just take the one away from the other one and divide by the one at rest, the one that we've observed on Earth. And then we can work out the recessional velocity, multiplying that by the speed of light. Okay, so in the video we've talked about the fact that the Doppler effect is observed in light, and we call that the redshift. And that happens where stars are moving away from us, or we can get a blue shift if the stars or galaxies are moving towards us. And we've calculated what the redshift is, and we've calculated the velocity, the recessional velocity, the velocity that they are receding, going away from us, of these galaxies and stars based on that redshift, because that is equal to the redshift multiplied by the speed of light.